विद्यार्थियों, तुहाडा आज दी क्लास फिजिक्स प्रैक्टिकल विच स्वागत है। आज असीं सर्ल्स एपरेटस की हैल्प नाल यंग्स मॉडुलस ऑफ इलास्टिसिटी की मैजरमेंट लई एक्सपैरीमेंटल मैथड ते विचार करांगे। डू यू नो what are perfectly elastic bodies? ਉਹ ऑब्जेक्ट्स जो कि डिफॉर्मिंग फोर्सेस ਨੂੰ रिमूव ਕਰਨ ਤੋਂ ਬਾਅਦ ਪੂਰੀ ਤਰ੍ਹਾਂ ਆਪਣੀ ओरिजिनल कंडीशन ਵਿੱਚ ਆ ਜਾਂਦੀਆਂ ਹਨ ਨੂੰ परफेक्टली इलास्टिक बॉडीज़ कहा जाता है। दूजे पासे ਉਹ ऑब्जेक्ट्स जो वापस अपनी थां ते आउण दी कोई टेंडेंसी नहीं रखती ਨੂੰ परफेक्टली प्लास्टिक बॉडीज़ कहा जाता है। असल विच साडे कोल कोई भी परफेक्टली इलास्टिक ਜਾਂ परफेक्टली प्लास्टिक बॉडीज़ नहीं है। ਜਦੋਂ ਕਿਸੇ ਬੋਡੀ ਨੂੰ ਕਿਸੇ ਹੋਰ ਬੋਡੀ ਨਾਲ ਕੰਪੇਅਰ ਕੀਤਾ ਜਾਵੇ ਤਾਂ ਇਹ ਵੱਧ ਇਲਾਸਟਿਕ ਜਾਂ ਪਲਾਸਟਿਕ ਹੋ ਸਕਦੀ ਹੈ। ਡੂ ਯੂ ਨੋ ਦ ਕੌਜ਼ ਆਫ ਇਲਾਸਟਿਸਿਟੀ? ਅਸੀਂ ਜਾਣਦੇ ਹਾਂ ਕਿ ਇੱਕ ਸੋਲਿਡ ਦੇ ਵਿੱਚ ਹਰ ਐਟਮ ਜਾਂ ਮੋਲੀਕਿਊਲ ਆਲੇ ਦੁਆਲੇ ਦੇ ਐਟਮ ਜਾਂ ਮੋਲੀਕਿਊਲ ਨਾਲ ਸਰਾਊਂਡਡ ਹੁੰਦਾ ਹੈ। ਇਹ ਆਪਸ ਵਿੱਚ ਇੰਟਰ ਐਟੋਮਿਕ ਜਾਂ ਇੰਟਰ ਮੋਲੀਕਿਊਲਰ ਫੋਰਸਿਸ ਨਾਲ ਐਮਬੈਡਡ ਹੁੰਦੇ ਹਨ ਅਤੇ ਸਟੇਬਲ ਇਕੁਇਲਿਬ੍ਰੀਅਮ ਪੋਜੀਸ਼ਨ ਵਿੱਚ ਰਹਿੰਦੇ ਹਨ। ਜਦੋਂ ਇੱਕ ਸੋਲਿਡ ਨੂੰ ਡਿਫਾਰਮਡ ਕੀਤਾ ਜਾਂਦਾ ਹੈ ਤਾਂ ਐਟਮਸ ਜਾਂ ਮੋਲੀਕਿਊਲਸ ਆਪਣੀਆਂ ਇਕੁਇਲਿਬ੍ਰੀਅਮ ਪੋਜੀਸ਼ਨਸ ਤੋਂ ਡਿਸਪਲੇਸ ਹੋ ਜਾਂਦੇ ਹਨ, ਜਿਸ ਕਾਰਨ ਇੰਟਰ ਐਟੋਮਿਕ ਜਾਂ ਇੰਟਰ ਮੋਲੀਕਿਊਲਰ ਡਿਸਟੈਂਸਿਸ ਵਿੱਚ ਚੇਂਜ ਆ ਜਾਂਦਾ ਹੈ। ਜਦੋਂ ਡਿਫਾਰਮਿੰਗ ਫੋਰਸ ਨੂੰ ਰਿਮੂਵ ਕਰ ਲਿਆ ਜਾਂਦਾ ਹੈ ਤਾਂ ਇੰਟਰ ਐਟੋਮਿਕ ਫੋਰਸਿਸ ਉਹਨਾਂ ਨੂੰ ਵਾਪਸ ਉਹਨਾਂ ਦੀ ओरिजिनल ਪੋਜੀਸ਼ਨਸ ਵਿੱਚ ਲੈ ਜਾਂਦੀਆਂ ਹਨ। ਇਸ ਕਰਕੇ ਬੋਡੀ ਆਪਣੀ ओरिजिनल ਸ਼ੇਪ ਅਤੇ ਸਾਈਜ਼ ਅਟੇਨ ਕਰ ਲੈਂਦੀ ਹੈ। आओ एक स्प्रिंग बॉल सिस्टम की हेल्प के नाल रेस्टोरिंग मैकेनिज्म ਨੂੰ विजुलाइज करिए।
Here the balls represent atoms and springs represent interatomic forces. When we displace any ball from its equilibrium position, the spring system tries to restore the ball back to its original position. In this way, we can explain the microscopic elastic behavior of solids.
Do you know what is stress? When a force is applied on body, it is deformed to a small or large extent depending upon the nature of the material of the body and the magnitude of the deforming force. However, the deformation may not be noticeable visually in many materials, but it is there. When a body is subjected to a deforming force, a restoring force is developed in the body. This restoring force is equal in magnitude but opposite in direction to the applied force. The restoring force per unit area is known as stress.
Let us consider F is the force applied and A is the area of cross-section of a cylindrical rod. Then magnitude of the stress is equal to F by A. Let the original length of the cylindrical body be L and the change in the length be delta L. Then the longitudinal strain is equal to delta L upon L.
1676 ਵਿੱਚ ਇੰਗਲਿਸ਼ ਫਿਜ਼ਿਸਿਸਟ ਰॉबर्ट हुक ने स्प्रिंग्स ਤੇ ਇੱਕ ਐਕਸਪੈਰੀਮੈਂਟ ਕੀਤਾ ਅਤੇ ਪਤਾ ਲਗਾਇਆ ਕਿ elongation mean change in the length produced in a body is proportional to the applied force or load. On the basis of his experiment, he presented his law of elasticity, which is also called as Hooke's law. According to Hooke's law, for small deformations, the stress and strain are proportional to each other. That is, stress is proportional to strain, or stress is equal to K into strain, where K is the proportionality constant and is known as modulus of elasticity. Tensile stress ਤਹਿਤ ਦਿੱਤੇ ਗਏ ਮਟੀਰੀਅਲ ਲਈ ਸਟ੍ਰੈਸ ਅਤੇ ਸਟ੍ਰੇਨ ਦੇ ਰਿਲੇਸ਼ਨ ਦਾ ਐਕਸਪੈਰੀਮੈਂਟਲੀ ਪਤਾ ਲਗਾਇਆ ਜਾ ਸਕਦਾ ਹੈ। ਸਪੋਜ਼ ਯੂਨੀਫਾਰਮ ਕ੍ਰਾਸ ਸੈਕਸ਼ਨਲ ਏਰੀਆ ਵਾਲੀ ਇੱਕ ਵਾਇਰ ਨੂੰ ਇੱਕ ਰਿਜਿਡ ਸਪੋਰਟ ਤੋਂ ਸਸਪੈਂਡ ਕੀਤਾ ਗਿਆ ਹੈ ਅਤੇ ਇਸ ਦੇ ਦੂਸਰੇ ਸਿਰੇ ਤੇ ਇੱਕ ਲੋਡ ਨਾਲ ਇਸ ਨੂੰ ਸਟ੍ਰੈਚ ਕੀਤਾ ਗਿਆ ਹੈ। ਜਿਵੇਂ ਜਿਵੇਂ ਅਸੀਂ ਲੋਡ ਨੂੰ ਇਨਕਰੀਜ਼ ਕਰਾਂਗੇ ਤਾਂ ਇਸ ਦੇ ਨਾਲ ਵਾਇਰ ਦੀ ਲੈਂਥ ਵੀ ਇਨਕਰੀਜ਼ ਹੁੰਦੀ ਜਾਵੇਗੀ। ਵੱਖ-ਵੱਖ ਸਟੇਜਸ ਤੇ ਸਟ੍ਰੈਸ ਅਤੇ ਕੋਰਸਪੋਂਡਿੰਗ ਸਟ੍ਰੇਨ ਦੀ ਵੈਲਿਊਜ਼ ਰਿਕਾਰਡ ਕਰਨ ਤੇ ਅਸੀਂ ਇਹਨਾਂ ਵਿਚਕਾਰ ਇੱਕ ਗ੍ਰਾਫ ਬਣਾ ਸਕਦੇ ਹਾਂ। ਆਓ ਇੱਕ ਐਕਟੀਵਿਟੀ ਤੇ ਨਜ਼ਰ ਮਾਰੀਏ ਜਿਸ ਵਿੱਚ ਯੂਨੀਫਾਰਮ ਕ੍ਰਾਸ ਸੈਕਸ਼ਨ ਵਾਲੇ ਇੱਕ ਹੈਲੀਕਲ ਸਪ੍ਰਿੰਗ ਨੂੰ ਰਿਜਿਡ ਸਪੋਰਟ ਤੋਂ ਸਸਪੈਂਡ ਕੀਤਾ ਗਿਆ ਹੈ।
In this activity, the fractional change in length, that is, the strain and the applied force needed to cause the strain, are recorded. The applied force is gradually increased in steps, and the change in length has been noted. A graph is plotted between the stress, which is equal in magnitude to the applied force per unit area, and the strain produced. We get a typical graph for the given metal. However, the stress-strain curves vary from material to material. These curves help us to understand how a given material deforms with increasing loads. From the graph, we can see that in the region between O to A, the curve is linear. In this region, Hooke's law holds good. In this region, the body regains its original dimensions when the applied force is removed, and the solid behaves as an elastic body, whereas in the region from A to B, stress and strain are not proportional, even though the body still returns to its original dimension when the load is removed. The point B in the curve is known as yield point or elastic limit, and the corresponding stress is known as yield strength of the material. When the load is further increased, the stress exceeds the yield strength and strain increases rapidly even for a small change in stress. The same has been shown as the curve between B and C. When the load is removed, at any point between B and C, the body does not regain its original dimension. In such case, even when the stress is zero, the strain is not zero. The deformation is said to be plastic deformation. The point C on the graph shows the ultimate stress of the material. Beyond this point, additional strain is produced even by a reduced applied force, and a fracture occurs at point D. The point D on the graph shows the fracture stress or breaking stress of the material.
We know that the ratio of stress and strain is known as modulus of elasticity, and this can be measured from the slope of OA region, that is, the proportional region within the elastic limit of the stress-strain curve. The ratio of stress to the longitudinal strain is defined as Young's modulus and is represented by the symbol Y. On substituting the values of stress and strain, we get Y equal to F by A upon delta L by L, that is Y equal to F L upon A delta L. Let's now discuss a method for the determination of Young's modulus of the material of a wire. आओ ਹੁਣ ਟੈਂਸ਼ਨ ਤਹਿਤ ਵਾਇਰ ਦੇ ਇੱਕ ਮਟੀਰੀਅਲ ਦੇ ਯੰਗਸ ਮੋਡੂਲਸ ਦਾ ਪਤਾ ਲਗਾਉਣ ਲਈ ਇੱਕ ਐਕਸਪੈਰੀਮੈਂਟਲ ਅਰੇਂਜਮੈਂਟ ਵੇਖੀਏ। ਇਸ ਵਿੱਚ ਸੇਮ ਲੈਂਥ ਦੀਆਂ ਦੋ ਸਟ੍ਰੇਟ ਵਾਇਰਸ ਅਤੇ ਉਹਨਾਂ ਦਾ ਕ੍ਰਾਸ ਸੈਕਸ਼ਨ ਏਰੀਆ ਵੀ ਇਕੁਅਲ ਹੈ ਨੂੰ ਨਾਲ ਰਿਜਿਡ ਸਪੋਰਟ ਤੋਂ ਸਸਪੈਂਡ ਕੀਤਾ ਗਿਆ ਹੈ। ਇੱਥੇ ਇਕੁਅਲ ਏਰੀਆ ਆਫ ਕ੍ਰਾਸ ਸੈਕਸ਼ਨ ਦਾ ਮੀਨ ਹੈ ਇੱਕੋ ਜਿਹਾ ਰੇਡੀਅਸ। ਇਸ ਅਰੇਂਜਮੈਂਟ ਵਿੱਚ ਇੱਕ ਵਾਇਰ ਨੂੰ ਰੈਫਰੈਂਸ ਵਾਇਰ ਜਾਂ ਆਕਸਿਲਰੀ ਵਾਇਰ ਕਿਹਾ ਗਿਆ ਹੈ ਜਿਸ ਤੇ 1 ਮਿਲੀਮੀਟਰ ਮੇਨ ਸਕੇਲ M ਅਤੇ weight ਰੱਖਣ ਲਈ ਇੱਕ ਪੈਨ ਹੈ। ਦੂਜੀ ਵਾਇਰ ਨੂੰ ਐਕਸਪੈਰੀਮੈਂਟਲ ਵਾਇਰ ਕਿਹਾ ਗਿਆ ਹੈ ਜਿਸ ਵਿੱਚ ਜਾਣੇ ਹੋਏ weights ਨੂੰ ਰੱਖਣ ਲਈ ਇੱਕ ਪੈਨ ਹੈ। ਐਕਸਪੈਰੀਮੈਂਟਲ ਵਾਇਰ ਦੇ ਬਾਟਮ ਤੇ ਇੱਕ ਪੁਆਇੰਟਰ ਨਾਲ ਇੱਕ ਵਰਨੀਅਰ ਸਕੇਲ ਨੂੰ ਲਗਾਇਆ ਗਿਆ ਹੈ ਅਤੇ ਮੇਨ ਸਕੇਲ M ਨੂੰ ਰੈਫਰੈਂਸ ਵਾਇਰ ਨਾਲ ਫਿਕਸ ਕੀਤਾ ਗਿਆ ਹੈ। ਇਸ ਐਕਟੀਵਿਟੀ ਵਿੱਚ ਪੈਨ ਵਿੱਚ ਰੱਖੇ ਗਏ weights ਥੱਲੇ ਵੱਲ ਫੋਰਸ ਲਾਉਂਦੇ ਹਨ ਜਿਸ ਕਾਰਨ ਐਕਸਪੈਰੀਮੈਂਟਲ ਵਾਇਰ ਵਿੱਚ ਖਿਚਾਅ ਹੁੰਦਾ ਹੈ ਜੋ ਕਿ ਟੈਂਜ਼ਾਈਲ ਸਟ੍ਰੈਸ ਕਾਰਨ ਹੈ। ਵਾਇਰ ਦੀ ਲੈਂਥ ਵਿੱਚ ਇਨਕਰੀਜ਼ ਨੂੰ ਵਰਨੀਅਰ ਅਰੇਂਜਮੈਂਟ ਨਾਲ ਮੈਜ਼ਰ ਕੀਤਾ ਜਾਂਦਾ ਹੈ ਪਰ ਅਸੀਂ ਐਕਟੀਵਿਟੀ ਨੂੰ ਇੱਕ ਸਿੰਗਲ ਵਾਇਰ ਨਾਲ ਵੀ ਕਰ ਸਕਦੇ ਹਾਂ ਪਰ ਰੈਫਰੈਂਸ ਵਾਇਰ ਦੀ ਵਰਤੋਂ ਲੈਂਥ ਵਿੱਚ ਕਿਸੇ ਵੀ ਚੇਂਜ ਨੂੰ ਕੰਪਨਸੇਟ ਕਰਨ ਲਈ ਕੀਤੀ ਜਾਂਦੀ ਹੈ ਜੋ ਕਿ ਰੂਮ ਦੇ ਟੈਂਪਰੇਚਰ ਵਿੱਚ ਚੇਂਜ ਕਾਰਨ ਹੋ ਸਕਦੀ ਹੈ। ਇਸ ਲਈ ਟੈਂਪਰੇਚਰ ਦੇ ਕਾਰਨ ਰੈਫਰੈਂਸ ਵਾਇਰ ਦੀ ਲੈਂਥ ਵਿੱਚ ਕੋਈ ਵੀ ਚੇਂਜ ਐਕਸਪੈਰੀਮੈਂਟਲ ਵਾਇਰ ਵਿੱਚ ਚੇਂਜ ਇਕੁਅਲ ਹੋਵੇਗੀ। Both the reference and experimental wires are given an initial small load to keep the wires straight and the vernier reading is noted. When the experimental wire is gradually loaded with more weights, which brings the wire under a tensile stress and the vernier reading is noted again. The difference between two vernier readings gives the increase in length produced in the wire. Let R be the initial radius and L be the initial length of the experimental wire. Then the area of cross section of the wire would be pi r square. Let M is the mass due to which there is an increase in length of the wire equal to delta L. Then the applied force is equal to mg, where g is the acceleration due to gravity. From the expression for the Young's modulus of the material of the experimental wire, that is y equal to Fl upon A delta L, we get y equal to mgl upon pi r square delta L. Let us now find out the Young's modulus of a given wire. Objective for this activity is to determine Young's modulus of the material of the wire using Searle's apparatus.
Apparatus required for this experiment are dead weight, slotted weight, screw gauge, meter scale, and a Searle's apparatus. The Searle's apparatus consists of steel wires, spirit level, pitch scale, spherometer screw, and hangers. Let us have a look on the block diagram of Searle's apparatus. It has an experimental wire of length L. With load, its length becomes L plus delta L, and the radius of the wire is R. Theory: if a wire of length L and radius R be loaded with a weight mg, then normal stress would be mg upon pi r square, and the longitudinal strain would be delta L by L, where delta L is the increase in length. From the expression for the Young's modulus of the material of the experimental wire, that is, y equal to Fl upon A into delta L, we get y equal to mgl upon pi r square delta L. Procedure: take two steel wires of same length and diameter and tie their ends in torsion screws. We measure the radius of the wire using screw gauge. First of all, we determine the least count of the screw gauge. To find the least count, give one complete rotation to the screw, and the distance moved by the screw on the linear scale is equal to the pitch of the screw gauge. Here, the pitch is equal to 0.5 millimeter. Circumference of the circular cap is divided into 100 divisions. That is, number of divisions on circular scale is 100. Hence, the least count of the screw gauge is 0.005 millimeter or 0.0005 centimeter. We know that due to wear and tear in the instrument, the zero mark of the circular scale does not coincide with the zero of the pitch scale. Then, the instrument is said to have a zero error. To find the zero error, rotate the screw forward till the spindle face of the screw touches the anvil face of the screw gauge, and edge of the circular cap comes on the zero mark of the linear scale. Here, fifth mark of the circular scale coincides with the reference line. Hence, zero error is plus 0.025 millimeter or 0.0025 centimeter. The corresponding zero correction is minus 0.0025 centimeter. To find the diameter of the wire, place the wire over the anvil face and rotate the screw using the ratchet head towards the anvil face and stop when ratchet slips without moving the screw. Note the number of division of the linear scale which is visible and uncovered by the edge of the cap as linear scale reading. It is 0.1 centimeter. Note the number of division of the circular scale lying above the reference line. Here it is the 61st division of the circular scale. Record the values of linear scale and circular scale and calculate the screw gauge reading. Here, the value of the diameter of the wire D0 is 0.1 plus 61 into 0.0005, that is 0.1305 centimeter. When we apply zero correction, we find that the mean corrected diameter of the given wire D is 0.1280 centimeter. Repeat these steps after rotating the wire by 90 degrees for measuring the diameter in a perpendicular direction. Again, record the corresponding values of linear scale and circular scale. Again, linear scale reading is 0.1 centimeter and circular scale reading is the 61st division of circular scale. Hence, the value of the diameter of the wire D0 is 0.1 plus 61 into 0.0005, that is 0.1305 centimeter. After applying the zero correction, we find that the mean corrected diameter of the given wire D is 0.1280 centimeter. Hence, the corrected radius of the wire is 0.640 centimeter.
Suspend weights from the hooks of both the frames so that both the wires are stretched and become free from kinks. Then load and unload kilogram weights on the hanger of the experimental wire to remove its fatigue and to prepare it for the experiment. To keep the reference wire taut, attach only a constant weight on the corresponding hook. Measure the length of the experimental wire from the point where it leaves the fixed support to the point where it is fixed in the frame. In this experiment, it is 215 centimeter. To find the least count of the micrometer attached with the Learles apparatus, we give one complete rotation to the screw and the distance moved by the screw on the linear scale is equal to the pitch of the micrometer. Here, pitch is equal to 1 millimeter or 0.1 centimeter. Circumference of the circular cap is divided into 100 divisions. That is, number of divisions on circular scale is 100. Hence, the least count of the micrometer is 0.001 centimeter.
Suspend 1 kg dead load from the hook of right frame, that is, from reference wire. Then, suspend 1 kg hanger from hook of left frame, that is, from experimental wire. Now, adjust the spherometer screw such that the bubble in the spirit level is exactly in the center. Note the reading of the spherometer as the reading for zero loads. It is 0.415 centimeter. Gradually increase the load on the hanger of the experimental wire by slipping a 500 gram weight in the hanger. In this condition, the bubble shifts from the center. Then rotate the spherometer screw to bring back the bubble in the center. To avoid backlash error, the final adjustment should be made by moving the screw in the upward direction only. If at any time the screw is raised too much, lower it below the central position and then raise it slowly to the proper position. Then note the reading against 500 gram load in the observation table. Here it is 0.402 centimeter. Repeat the activity for all of the slotted weights up to 2500 gram. Observations and calculations. First, we measure the extension in wire delta L for different loads. To calculate coefficient of Young's modulus of the given wire, draw a graph between load and extension in wire. Choose the scale on x-axis as 1 centimeter equal to 0.5 kilogram weight of load, and on y-axis 1 centimeter equal to 0.01 centimeter of extension. You can see that the graph we obtained is a straight line graph, and the slope of the graph, that is delta L by m, is 0.025 centimeter per kilogram weight.
Since the length of the experimental wire is equal to 215 centimeter, for 1 kilogram weight, extension in the wire is 0.025 centimeter. Since the radius of wire is 0.0640 centimeter, hence the Young's modulus of the given wire would be 1 into 9.8 into 2.15 divided by the products of 3.14, square of 0.00064 and 0.00025. Therefore, y is equal to 6.55 into 10 raised to the power 10 Newton per square meter. Young's modulus of the given wire is 6.55 into 10 raised to the power 10 Newton per square meter. Load versus extension graph shows that stress is proportional to strain. Let us have a look on the precautions to be incorporated for these experiments. To avoid undue pressure, the screw of the screw gauge should be always rotated by ratchet and not by cap. The screw should move freely without friction. The zero correction with proper sign should be noted very carefully and should be incorporated. For same set of observations, the screw should be moved in the same direction to avoid backlash error of the screw. Excessive rotation should be avoided. At each place, the object should be measured in two perpendicular directions if possible, and then the mean of the two be taken. Readings should be taken at least for 5 different places equally spaced along the whole length or the surface of the given object. Error due to parallax should be avoided. Both the wires, experimental and auxiliary, should be similar. Kings should be removed before starting the experiment. Both the wires should be supported from same rigid support. Add or remove slotted weights gently. We should wait 2 minutes after adding weights. To avoid backlash error, the screw should always be turned in the same direction. On the other hand, there may be some sources of error. Care should be taken for such errors also. The screw may have friction. The screw gauge may have backlash error. Circular scale divisions may not be of equal size. Given wire may not have a uniform area of cross section throughout its length. The diameter of the wire may decrease when loaded. The slotted weights may not be standard weights. ਹੁਣ ਅਸੀਂ ਅੱਜ ਦੇ ਵਿਸ਼ੇ ਦੇ ਅਖੀਰ ਤੇ ਆਉਂਦੇ ਹਾਂ ਅਤੇ ਨਾਲ ਹੀ ਕੁਝ ਕੁਐਸਚਨਸ ਪੁੱਛ ਕੇ ਇਹ ਪਤਾ ਕਰਦੇ ਹਾਂ ਕਿ ਅੱਜ ਦੇ ਟੌਪਿਕ ਵਿੱਚੋਂ ਤੁਹਾਨੂੰ ਕਿੰਨਾ ਕੁਝ ਸਮਝ ਆਇਆ ਹੈ। पहला क्वेश्चन है, what is the relationship between stress and strain? Is the answer, when a body is subjected to a deforming force, then stress is directly proportional to strain